Alright guys, welcome to the last unit of the year. This is going to be on chemical bonding. This is chapter 12 in your book. I'm going to break this unit up into 3 videos. The first video is going to be about drawing molecules, something that we call a Lewis structure. You guys have seen these before in biology. You actually see a variant of this sitting on the screen right now as a title slide. The second video is we're going to talk about polarity, so whether or not molecules will have positively and negatively charged ends, and what that can mean to some of the properties through something we call an intermolecular force, which you already, again, covered a little bit of that in biology. Your hydrogen bonding interaction, for example, is an intermolecular force. We're going to go over how to determine what forces a molecule has. And our third video, so our last assignment of the year, is we're going to take those intermolecular forces and start comparing multiple things. And for example, saying, here are 5 compounds, rank them from the lowest boiling point to the highest boiling point, and we'll be able to explain why. You guys are going to need your notebook. You're going to need something to write with. You will need a periodic table because we have to reference the number of valence electrons that something has. You won't need a calculator because the only math we're doing is addition and subtraction. So when you're ready, let's start. Okay, so to go over again the octet rule, I told you guys this rule was a little bit earlier in the year, but it's been a while. So the octet rule is basically the idea that everything wants to have a completely filled valence shell. Some atoms will gain electrons, some atoms will lose electrons, and other atoms will share electrons depending on the environment that they're in. Right, so metals will typically lose electrons. Very reactive nonmetals like to gain electrons. And there are sometimes that things will actually share electrons. That's going to be the main focus of what today's video is. Now, a filled valence shell is usually 8. Right, although for a couple of the smaller elements like hydrogen and helium, their first valence shell can only hold 2, so they only need 2. Now, an ionic bond is a type of bond that you form from a metal losing electrons becoming positive and a nonmetal gaining electrons becoming negative. And then you have this positive and negative charge interacting, and when they interact, that creates an attraction. Right. A covalent bond, you'll see a lot more often, is when 2 nonmetals try to bond with each other. Since neither of them really want to lose, what they're going to wind up doing is they're going to share electrons in order to get their way up to a filled valence shell. Now, the structures that I'm going to have you guys drawing are called dot structures, also known as Lewis structures. What these do is these show the structure of the molecule, so where the elements are in relation to each other, and how the electrons are distributed in this molecule. Now, the key thing when we're talking about dot structures is that these are based on the idea of pairs of electrons. The reason why is that a chemical bond is a pair of electrons that are shared between 2 atoms. Right? So we call those shared electrons a bonding pair. Now, when we start taking count of whether things obey the octet rule, bonding pairs count towards both. Right? So for example, if I said I had 2 hydrogen atoms, so hydrogen here, a pair of electrons, and then another hydrogen here. These 2 electrons in the center count for both hydrogens, so I can say each hydrogen atom has 2 electrons. Right, so 2 electrons, because these guys count for both. Now, you don't have to share just one pair of electrons. It is possible to share more than one pair. Right, so sharing more than one pair of electrons is something that we call a double bond. If you share 3 pairs of electrons, it is a triple bond. Right, so bonding can be either single, double, or triple. There are some very rare circumstances where you can form a quadruple bond, but there are only a handful of those that really exist, so we don't ever pay attention to them. So that's our first type of electron pair, a bonding pair between 2 atoms. The second type of pair is what we call a lone pair. A lone pair is something that only exists on one atom. Right, so, for example, let's say I have a nitrogen bonded to a hydrogen. Now, this dash right here just means a pair of dots. It's just an easier way of drawing a pair of dots instead of having to put them on there. But what we have here is this dash is a bonded pair, and this pair of dots here that's only on the nitrogen is a lone pair. Right, so lone pairs are only owned by one atom. So if I wanted to say this, in this case, this hydrogen has 2 electrons because of the bond. This nitrogen has 2 from the bond because it's shared, and 2 more for its lone pairs. So this would have 4. Right, so that's how we keep track of how many electrons things have on them. So we'll start off with some pretty simple molecules to work with. Right, now, one thing I should probably go over first is when you are drawing, right, so the number of dots for an atom is equal to the number of valence electrons. Right, so dots is equal to valence electrons. So the hydrogen atom has 1 valence electron. It's in group 1. Right, so if you take out your periodic table, remember what we said, valence electrons is equal to last digit of group number. Right, so hydrogen is in group 1, which means it has 1 valence electron. If I draw this dot, I just take hydrogen and I put a dot. Now, it doesn't matter whether I go top, bottom, left, or right in general. Right, so this is the easy way to draw the electron or the electron on hydrogen. Just H with 1 dot to represent its valence electron. Oxygen is in group 16 on your periodic table, so it has 6 valence electrons. Let me put in the other E here. Now, the way we would go about this is I'm going to draw my oxygen, and I'm going to go cardinal directions, so north, south, east, west, or top, bottom, left, right, whatever you prefer. I'm going to work around the circle once, and then I'm going to come back a second time. Right, so I get to put in 6 of these. So 1, 2, 3, 4, 5, 6. So notice here I have 2 pairs and 2 singles. Right, that's how I draw my 6 electrons in. If I was going to do 7, I'd make it 3 pairs. 8 would be full 4 pairs. Right, so this is how you go through and draw these for most atoms. Now we'll actually put these together and draw a simple molecule. Right, so water. The water molecule, I'm going to start off with oxygen. Oxygen has 6, so I'm just going to copy down 1, 2, 3, 4, 5, 6. Now again, one thing to keep in mind, top, bottom, left, right are all equivalent positions. It doesn't matter how you have the 2 pairs and the 2 singles as long as you have them somewhere. Alright, so now we will change the color a little bit to give you some contrast. We have hydrogen number 1 with its 1 electron, and then we have hydrogen number 2 with its electron. Right, so now what this does, these are being shared, right? So we have these 2 right here, which are bonded pairs or chemical bonds. And then we have the 2 electrons up top, which are our lone pairs. If I were to count, hydrogen has 1, 2 electrons. Since hydrogen only needs 2, it's good. This hydrogen, 1, 2, it's good. the oxygen. 1, 2 at the top, 3, 4 on the right, 5, 6 on the bottom, 7, 8 on the left. Oxygen has 8 electrons. It has a full octet, so it's good. Alright, so this is the dot structure for water. Now, another way I can do this, again, if I want to draw lines, is I just put an O, dash H, and then the two pairs. This is more commonly how you see water drawn. Again, top, bottom, left, right are all equivalent positions. It doesn't matter. Now we'll try some more simple ones here. Okay, so again, CH4. Carbon has 4 valence electrons. Hydrogen has 1. So I'm going to do carbon, 1, 2, 3, 4. Then we're going to do hydrogens with their 1. So 1, 2, 3, 4, which gives us this. Right, so that's methane. NCl3, nitrogen trichloride. Now, again, it's going to be a little bit more challenging here because we're going to have a lot more dots to work with. But nitrogen is in group 15, so it has 5 valence electrons. Chlorines are in group 17, so they each have 7. Right? Notice this is Cl. So I'm going to put nitrogen in the center. N with 1, 2, 3, 4, 5. I'm just shortcutting. Now we're going to come back here, do our chlorines. There are 3 of them. So I'm going to put a chlorine here, a chlorine here, a chlorine here. It gets 7, so there's only one open slot. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right, so this gives me N with Cl's and the pair on the N. So that's nitrogen trichloride. Right, so you can actually see how so some atoms have holes where you can put in electrons, and you can kind of see how they can combine for fairly simple molecules and make relatively easy to draw structures. Now let's look at CO2. For CO2, carbon has 4 valence, oxygen 6. Right, carbon's in group 14, so 1, 2, 3, 4. Now we come in and put in our oxygens. Oxygen, 1, 2, 3, 4, 5, 6. Oops, sorry. Let me actually erase that. And I'm actually going to get rid of that too, because I should not be having a line there. And then our other oxygen, 1, 2, 3, 4, 5, 6. Now here's the thing to notice. If I look at this molecule doesn't obey the octet rule, right? Because if I count up the oxygen here, 1, 2, 3, 4, 5, 6, 7. So that has 7. This is its mirror image also at 7. 1, 2, 3, 4, 5, 6 dots on the carbon in center. So that doesn't work out. That doesn't obey the octet rule. This is one of the problems that you get when you try to use this particular method for drawing Lewis structures. Right, for simple molecules it works, but once you get a little bit more complex, it breaks down a little bit. So what I'm going to give you are some actual rules that will always work.